Okay, so number 7. Next up is number 7, which says add or subtract, simplify by combining like radical terms if possible. Okay, so how do we add radicals? So we have 16 square root of 5 plus 2 square roots of 5. Well, these are called like radicals. See, these portions of the numbers are the same. Okay, so these are like radicals. If we call, for example, we can treat them as like if it was a variable a whose value was square root of 5, then we would have 16a and 2a's, right? And what do? You just, how many a's do we have in total? Well, 16 plus 2 is 18, right? So same with square roots. How many square roots of 5 do we have? Well, we have 18 roots of 5. So that's how you approach this problem. But again, you can only do that when these radical expressions are exactly the same. So we have kind of like the same variable. If we had, for example, 16 roots of 5 plus 2 roots of 7, these are not like radicals, so we cannot combine them anymore. That's it. They're different expressions. That's like 16a plus 2b. What do? Nothing. Then they don't combine. Okay, next on our list is number 9. Rationalize the denominator. Assume all variables represent positive numbers. Okay, so we have a square root of, oh, I skipped number 8, but we're gonna do it next. We have a square root of 49 over 5. So, and the square root covers both the numerator and the denominator. So the first thing that I want you to remember is that you can actually break it down. You can break up the square root. You can put the numerator into square root and then the denominator under the square root. Okay, now 49 is a perfect square, right? So we can square root it nicely. Again, remember it's positive 7, but what to do with square root of 5? Well, what we want to do, if we had square root of 5 squared, that would give us just 5 because root cancels out the square. Also, if we have square root of 5 squared like that, that would also cancel this, the square would cancel the square root, you would still get 5. So either way, either square under the root or square above the root, either way, it doesn't matter. But so how do we achieve that? Well, we need to multiply it by another square root of 5, right? So this way we get square root of 5 squared on the bottom. And that's what we want. That's what they say. That's what they mean when they say rationalize the denominator, because now in the denominator we have 5. Yay. But let's see what happens in the numerator. Okay, so the denominator is all squared away and we're happy. What happens in the numerator? Well, again, the rules of fractions say, well, we do to the denominator, we have to do the same to the numerator. So the numerator gains a factor of square root of 5 as well. So what do we have here? Well, it's going to be 7 roots of 5. Okay, and there is nothing we can do with it. It became irrational. So we traded off basically by rationalizing the denominator. So here our numerator was rational, and the denominator was irrational. So now we made our denominator rational, but the numerator is irrational. So we traded off. We did not eliminate the radical completely, but that's okay, because by the definition, the simplified fraction is the one with a rational denominator. In this case, it's not possible to make both numerator and denominator rational. Not possible. So, but we prefer to have a nice denominator. Why? There are several reasons for it. One of which is if I was to add this to another fraction, it's easier for me to find a common denominator, so forth. So yeah, by definition, simplified fraction is the one without radicals in the denominator. You can have radicals in the numerator. All right, so let's go back to number 8 that we skipped. And number 8 says, evaluate f of x for the given x value. So we have f of x equals x squared plus 1, and x equals 4. So what do you do? Well, when you have that, this is the function notation where x could be anything. Well, they told you x is 4. So that's what you do. You plug in 4 whenever you see x and evaluate. So f of x is going to be 4 squared plus 1. And that's going to be 16 plus 1, and that's 17. Okay, so easy. All right, so next we have number 10. Number 10, again, says rationalize the denominator. Wow, let's take a look at that. Okay, so here it is, written out. Now, this problem is a notch more complex than the one that we looked in, saw in number 9. Why? Because in number 9, our denominator was a monomial, and here is a binomial. We have 2 terms. We have a square root of 11, and we have 3 in the denominator. So in the previous problem, number 9, we would just multiply by the radical expression, right? But if we do it here, let's just explore it for a second. If we multiply by a root of 11 on the bottom, what's going to happen is we're going to bring it in, open the parenthesis, right? Because we multiply the entire denominator. We cannot just pick and choose and just multiply one term in the denominator. No, we cannot do that. We have to multiply entire denominator and then entire numerator as well. So let me just indicate that too, to remind you. Okay, but if we multiply the entire denominator, we're gonna open parenthesis, factor it in, right? So what's gonna happen is I'm gonna have this my square root of 11, the original one, and then multiply by the root of 11. Now I have root of 11 squared. Good, right? Because that's what I want. And then I have 3 multiplied by the root of 11. So what I did essentially, I got rid of the square root here. That's going to be just square root of 11 squared, which is just 11. But I picked up the root of 11 in my second term in the denominator. So I didn't get rid of it at all. So if I do it again, same thing happens. So no matter how many times I multiply by square root of 11, it will not go away just because one portion is square rooted and another one is not. But even if they both were square rooted, but different roots, like let's say root of 11 and a root of 5, we still wouldn't be able to use our technique that we use for number 9. So we have to come up with something else. And what comes handy here is a formula that hopefully you guys learned in intermediate algebra, and that's the multiplication of two binomials that look exactly the same, except the sign in between them is different. So in the first group, we have a plus, and in the second group, we have a minus. Such binomials are called conjugates of each other. Conjugates. So what happens when you multiply by two conjugates? So what happens, you're gonna end up with a squared minus b squared. It's called the difference of squares formula. Difference of squares. So everything gets squared, right? The both numbers gets squared. That would actually be very helpful here. So instead of multiplying by a single radical, we're gonna multiply by a conjugate. So let's try. So we started with square root of 7 and then root of 11 plus 3 on the bottom. So the conjugate of the denominator is going to be root of 11 minus 3, right? And again, I have to multiply that same thing to the numerator. Have to multiply it to the numerator. All right, so according to this formula, and by the way, if you have time on your hands, just go ahead and multiply, use a FOIL formula and FOIL method and see if you get this back. You should. But if we're just gonna apply this formula straight forward, and we're gonna get square root of 11 squared minus 3 squared. Okay, according to the formula. So what does it give us? Square root of 11 squared is 11, and 3 squared is 9. So 11 minus 9. So in the bottom, we have 2. We've rationalized the denominator. Yay. Now let's see what happens in the numerator. In the numerator, we have root of 7 times root of 11, and then plus root of 7 times a negative 3, right? Or minus 3 times root of 7. Okay, so we can put root of 7 and root of 11 under the same root. So it's gonna be a root of 7 times 11. So we have a root of 77 here. And then minus, we're just gonna move 3 to the front. 3 roots of 7. That's it. So it's root of 77 minus 3 roots of 7. Okay, so that's what it is. Our numerator became uglier. I give it to you guys. It's true. But our denominator became nice. So that's what we care about. All right. I'm gonna take a quick break and we're gonna finish numbers 10, numbers 11, 12, and 13 in the next video.